All right, so we've covered sampling distribution, confidence intervals, sample size, and the last thing is hypothesis testing. So just like before, we are now looking at testing a claimed value, so different than trying to estimate what the value might be. And we still have our 5 steps. First big change is that in our hypotheses, you'll note that now we're using mu, the true population mean or average, as opposed to p, the true population proportion. So same exact thing, we're still going to have an equal to in our null, and we'll have some direction associated with a keyword in our alternative, but we're going to change out what the parameter of interest is. Another note here is that usually it is easiest to spot. In the last section, right, we had the p, and sometimes we didn't have another competing proportion that we were worried about which one is the hypothesized value. We had like an x and an n, but now just know anytime we see the word sample, that's going to give us our x bar, which is not the value that goes into our hypotheses. That's our value that is our evidence that we're going to use to test that hypothesis. So just know there'll be 2 means running about, and you want to make sure that you're not including the one that was from the sample that we're using as our evidence. After that, we're going to calculate our test statistic. Now, instead of a z, our test statistic is going to be a t. This is going to be on the formula sheet. And then we're going to find a p-value based on that test statistic. So again, this is going to be using a table. However, now we're in a different table because we're not getting out a z-score, we're getting out a t-score. So we're going to use that t-table. As a note, for those of you with the graphing calculator, steps 2 and 3 can still be done in the graphing calculator. They will be done with the, not t-interval, goodness gracious, with t-test in your graphing calculator. However, you know that I like to have multiple choice questions that make sure you can do these things by hand. So you'll still want to stay with me and pay attention to the rest of this video. So we need to figure out how to use that t-table to find p-values. So that's exactly what our first exercise is here. So if a 2-sided hypothesis test, which we know means that we need to multiply our p-value by 2, was done for a sample of 20 people and a test statistic was found to be t is equal to negative 2.40, what is the corresponding p-value? So just like we did in class last week, we could draw a picture. We know that the t-distribution, just like our z-distribution, our standard normal distribution, is centered at 0. And in this case, we got out a negative 2.4. And this says it's a 2-sided or 2-tailed test. So we care about this. We also care about this because remember, it is symmetric. So those are the same. So when we're looking for our p-value, it's the area in both of those tails. Okay. And since we have a t, this means we need to go to the t-table. If we're going to go to the t-table, we need a degree of freedom, right? So that degree of freedom is equal to n minus 1. So in this case, our 20 minus 1 would give us 19. So let's go look at that table and figure out what the heck we're supposed to do here. So our degree of freedom, let me erase all this business. Our degree of freedom is 19. So we know we want to be in this row. Now we want tail probabilities, and there are actually 2 legitimate ways to do this. Remember this was our drawing, I'll redraw it here. 0, negative 2.4, positive 2.4, and we're looking at these tails. Remember the entire t-table is set up where all of the t's are in the middle here. So we want to figure out where 2.4 is. And unfortunately, 2.4 is not exactly in our table. 2.4 is somewhere between 2.2 and 2.5, a little closer to 2.5. So we're not going to get out an exact p-value using the table. We're going to get a range of p-values. So 2 ways you could do this. One, you could go down and then use the fact that your confidence level gives you that middle percentage and do a -1. I prefer, especially if we end up with one-tailed stuff later on, going upward to the tail probabilities, which is why the t-table is actually set up despite this one caveat of getting ranges, set up a little better for hypothesis testing because it only gives you half of the table and it only gives you tails, whereas the Z gives you both, and therefore you can make some mistakes with it. You will note that our original T given to us was negative, and I looked up a positive. That's because now we have right tails as opposed to the Z table where we had left tails. So you're always going to look up the positive for the T's instead of the negative, so we get a tail out. So our probabilities, or our upper tail probabilities, we know that this is somewhere between 0.01, I'll just call it tail probability, and 0.02. And we need to multiply that by 2. So that's exactly what we're going to do on our lecture notes. We're going to go over here and we're going to say, okay, this thing was 0.01 to 0.02. And since we knew it was times 2, I'll need to multiply those values by 2. So we won't get out an exact p-value, but we'll find out that our p-value is between 0.02 and 0.04, which is enough to make a decision, right? In fact, I think I asked you to do that next, so we'll do that in, yeah, we'll keep going. You could, by the way, do this with TCDF in a calculator. You have to use it sort of like you would use a normal CDF. So if I went here, you do not need to do this. In fact, if I have a multiple choice question, I will use the table. So you don't have to worry about doing this. But if you wanted to get an exact value, because I know for some people it's very annoying to have this weird range. So well, let's do it with the negative. Might as well, right? Negative E99 to our negative 2.4 they originally gave us. Degree of freedom was 19. And then take this thing and multiply it by 2. So we do get out a value, that 0.0268, that's between here. So if you wanted to write all that down, you could. I'm not going to, because I'm never going to use the calculator to do this again. I'm just going to use the table. All right, so step 4 is still making a statistical decision. Absolutely no differences here. And note that when you get out something like we had before, a p-value within a range, those upper tail probabilities in that table are always such that you can make a decision. In this case, if our alpha is 0.05, how does 5% compare to 4%? Well, our p-value will be lower and we reject the null. However, if we used an alpha of 0.01, now this p-value, every single value from 0.02 to 0.04 is greater, and we'd fail to reject the null. So as I was saying, you are in good shape in that this range will always be completely above or completely below our typical alpha levels of 0.1, 0.05, and 0.01. And then our conclusion, same exact thing at a 1% significance level. There is not enough evidence to conclude that the average blah, 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 blah. Big note here, make sure that you mention mean or average. That's a very common mistake, is that students just say that the amount of time that teenagers will spend online. It's not about the amount of time they'll spend online, it's about the average amount of time they'll spend online. And then, of course, having units there. So those are the two most, the biggest oversights. If you just talk about teens spending time online, you're not saying that word average, and you're actually saying something incorrect.